everyone, welcome to the Energy of Kinetics, which is episode 16 in a long series of episodes on kinetics. We started on episode 10 and now we're on 16, so if you haven't watched 10 through 15, please stop, go back and do so, and then you'll be ready for this one. So Energy of Kinetics is something that is super interesting because we are now taking what we formerly described as energy, which is in the thermodynamics category, and we're kind of blending the two categories. So in my opinion, what's really neat about episode 16 is we're taking thermo and we're trying to find a way to connect it with kinetics. Okay, so that's the point of this whole episode. So before I get really deep into the thermo component of it yet, I want to start off by talking about our 4 factors that actually affect the speed of a reaction or the rate of your reaction. So the number one, the first thing that we already talked about in episode 10, that was the very first thing I taught you about kinetics, is that concentration will definitely affect the rate of the reaction. So what it says here is that the higher concentration increases the frequency of collisions. So as the collisions go up, that means our concentration is up, or as a result of our concentration, I should say, and therefore that results in a faster reaction. So the way I like to think about this is that when we have an increase in the concentration of A, remember we just use A in kinetics for our sample molecule, then that means that we're going to have an increase in our rate. Okay, so that's the very first thing that we talked about. Now number 2. The second thing that can affect the rate of a reaction is its medium. And medium is technically the way I want you to think about it, but a lot of people translate that into the nature of the reactant. And when we talk about the nature, we're really talking about the phase. So let me read our example for you here. So a solid reactant with a large surface area actually offers more opportunities for reaction, but crushing it up into large chunks of solid into fine powder results in a faster reaction. So we give it more surface area. So the more surface area, the more spots, or I guess area really, for this place to have reactivity. And so the more area available or more the edges on a certain reactant, the more likely to have a reaction. Personally, when I think about this, I think back to my own research. So I did lots of kinetics and catalysis in lab. And when I talk about a medium, I'm thinking about the solvent that I'm using. And so I like to think about it in terms of viscosity. So for example, if I had a bunch of reactants and I put it into a swimming pool or a beaker, right? And I was trying to have them collide or measure how quickly they collide or they interact with each other, the best case scenario would be to put them into a solvent that is not very viscous, like water, okay? So let's say that in water, I can have my 2 reactants interact in a matter of like 5 seconds. I'm just making a bullshit number here, okay? But like 5 seconds. Then instead of water, we're gonna take that out and we're gonna put in something a little bit thicker, like ethylene glycol. So in your head, think like jelly, right? Or jam, that kind of consistency. Now think about how long it's going to take for those 2 reactants to interact, right? It's going to be harder. They're going to have to like physically swim through the pool to get to each other and actually have that collision. So if water took 5 seconds, something a little bit more viscous would take 10 seconds. Well, now if we up the viscosity even more and get it to more of a polymeric solution, something that's really thick, think like Jell-O in your head, that's going to take forever. It's going to be super hard for the molecules to actually like maneuver through the solvent to get from one place to the other. So 5 seconds, 10 seconds, this would be like 100 seconds. So the medium, or the actual nature of the reactants, how easily they can interact with each other, that really is going to affect the rate of the reaction. Number 3, temperature, and that's really what we're going to talk about today. Temperature is one of those ways that we can combine kinetics and thermodynamics, and so we're going to kind of use that as a way to route through. Now for temperature, what we have here is that your reactant molecules have more energy at higher temperatures. We know this. You could have told me this in Unit 1 of General Chemistry 1. So a larger number of reactant molecules can get over the activation energy hump. So by the end of this episode, I want you to be able to understand what that last piece means. So if the hotter something is, it means that the reactant molecules have more energy, right? You know this part. And then if they have more energy, they can actually get over an activation energy. I like the word barrier instead of hump. And think of it like a big hill. So the bigger the hill, the more energy you're going to need to get over that hill before the reaction can actually start. But that's the point of today's episode, so we'll get there in just a minute. And then just a preview of our last episode. We have one more after this for kinetics, and that's on catalysis, and that is the 4th thing that changes the rate of the reaction. So catalysts speed up the rate of a reaction, but they're not actually used up in the reaction. we talked about that in the last episode for mechanisms, where we talked about how a catalyst is something that is added in the beginning and then it's regenerated at the end of the mechanism, so that we can have this like cyclical approach and the catalyst can continue to have the reactivity or encourage reactivity. So catalysts are up next, but we just need to know that there's 4 different ways, or you need to know that there's 4 different ways that we can affect the rate of the reaction. So concentration, temperature, medium, and catalyst here. Those are your 4. So now this brings me to an Arrhenius plot, and this is something that if we were having free responses this year, we would definitely ask you to draw out, but you lucked out here, so you're probably just going to have to interpret it, but you still need to know what it is. So we're going to start off by drawing an endothermic process. Okay, so endothermic, this was last semester's topic, you already know this, so I'm just going to draw this right in. We're going to have R here for our reactant, and then I'm going to come over here kind of like midway for P for my product. And so formally, last semester, you would have been able to tell me that my products minus reactants right here, that's going to be my enthalpy. And because my products minus reactants is going to give me a positive value, I know that this is an endothermic process. However, that's thermo, okay? So that's the thermo component. They're like straight up just energy of reactants and products and da-da-da-da-da. We already did this. Now what I want to do is add the kinetic piece. So in order for our reactants to get to our products, not only do they need to go from low energy to high energy, they actually have to go over an energy barrier first, then they can get to the products. So we like to draw it kind of like this. So it goes up and then curves down a little bit more like that, okay? So this part down here, thermo, that's your enthalpy. But above that, here, and then actually you're going to go all the way down to this reactant level. So peak minus reactant level, that is EA, and that is called your activation energy. And we're going to talk more about that in a little bit. But essentially, it's the bare minimum energy needed in order to go from A to B, from reactant to product. This should sound kind of familiar to you because we talked about the photoelectric effect way back in the day at Unit 2 in first semester. Remember how there was like a bare minimum threshold energy needed to eject an electron? This is a similar process. There's a bare minimum energy needed in order for this to go from a reactant to product. So it's always, we're always talking about that like bare minimum energy. That's what your activation energy barrier is. Now this is the kinetics component, okay, kinetics. And that's going to be in unit of joules. So this is what I have for an endothermic process. I also want to label that at the very top here, we have what's called our transition, and we're going to talk about our transition state. We're going to talk about that in just a little bit, but for right now, I want you to label it like this. Okay, so your transition state is what happens in the middle when you go from reactant to product. But let's look at exothermic first. So I'm going to give you like just a couple seconds here. If you want to, you can pause the video and go ahead and redraw this right now for yourself. See if you could do it after doing endothermic. That's what I would have asked you to do in class. You can pause it. But just for the sake of your time, I'm going to go ahead and draw it for you. So we know exothermic goes from high energy reactant to lower energy product. Okay, but that's our thermal component. So products minus reactants is going to be right here. Again, that's our enthalpy component, so delta H. We're exothermic, so we know products minus reactants is going to be a negative term. Again, that's our thermo. So now what we're going to do is put some kinetics on that. And now this activation energy barrier doesn't really have to be that high. It can be like this. It could also be much higher. It could go all the way up here. It really doesn't matter, okay? But well, I mean, it does matter for the reaction. Okay, but now what I want to do is focus on this part up here. So this is our transition state. So your transition state is what is formed when you go from your reactant to your product. But I want to be super, super clear. That is not the same thing as the intermediate that we talked about in the last episode. Okay, so an intermediate is something that is a reactant first and then it is a product. Here you can see that our transition state is not in the products. Okay, it is above the products, it's before the products, it is what happens in the middle. So I like to think about it as like when you're changing an outfit, right? So you're going from reactant to product, you're going from pants to a dress, whatever, okay? So when you do this, you're like changing your outfit. So your transition state is where you're in the middle of it. You're like, you've got your shirt on, but then you've got the socks on, or your shoes are on for one thing and your shirt's on from the other outfit. So you're combining outfits, if you will. And the same thing here, you're combining molecules. So you could have some atom that has like 5 or 6 bonds, even though that totally breaks the octet rule. And that's just because it's in this like intermediate state. It's not an intermediate though, but it's in a middle state. So you have to be super careful about that and make sure you understand the difference. So transition state here, not a solid molecule. I could not reach in and like pull that out of my flask. That doesn't happen. It's not like a stable product. So this thing forms and then moves right into a product. Does that make sense? Hopefully. Okay. Last thing I want to do is label your activation energy barrier here. It's always going to be from the peak down to your reactant. So this one is much, much smaller. And that's another reason why it's super, super easy, or I would say very likely, for exothermic reactions to occur. They don't need a very high activation energy barrier because we're already going from a higher energy reactant down to a product. So this is how kinetics and thermo come together, but we're going to talk about this all the live long day, so don't worry if it's not super clear yet. All right, so I'm going to give you a second here to answer a question. Here we go. At a given temperature, the molecules in a sample are what? Do they have the same energy, distribution of energies, or have one of several fixed energies? Take a second here, come up with an answer. At a given temperature, the molecules in a sample have a distribution of velocities. If you're my students, hopefully you were screaming that because you knew the answer, because we've talked about it pretty much every month since I met you. But for everybody else, let's make sure we're on the same page here. So at a given temperature, the molecules in a sample have a distribution of energies. That is because temperature is a measurement of the average kinetic energy. So in my very room right here, I've got tons of molecules swirling around me, and they all have a variety of different kinetic energies. They're close to each other because we can assume in this small room that it's all at the same temperature, but they're not identical. So if they have a variety of kinetic energies, what that really means is they have a variety of different velocities. And if they have a variety of different velocities, that's really saying they're moving at different speeds. So why does this matter when we're talking about kinetics? Well, it has to do with collisions. So if the question is, how many molecules actually have enough energy to get over the barrier? So I want to look at this graph. What we have here on our y-axis is our number of particles, okay, our number of particles, and then on our x-axis we have our energy down here. And what we're plotting are two different samples at different temperatures, okay? We should assume it's the same gas though, or molecule, whatever it is we're talking about, same reaction. So the first thing I want to point out is that our temperature 1, T1, is colder than T2, okay? Blue versus red, that's why it's color-coded that way. So let's look at T1 first. What we see is that we have a small amount of particles down here on this side, on the right side of this line that's imposed, whereas our red line has a lot more. So let's actually look at this line right here and see what that means. So I'm going to draw this all the way through. If you're taking notes too, draw it all the way down to the bottom. Because what we can see is the molecules that are on the right side of this line, they actually have enough energy to react. These are the ones that have enough energy to react. Their kinetic energy is high enough, meaning their velocity is high enough, so they're having the enough collisions in order to move from reactant to product. Now on the other side of the line, on the left side, what we see is that these molecules, for whatever reason, are not moving fast enough. Their velocity is not high enough, which we can see in terms of temperature. So on the left side, we would say there's not enough energy. Okay, there's not enough energy to react, meaning that our reactants are not colliding enough with enough force, with enough energy at the right orientation in order to move from reactant to product. Okay, so let's keep looking at this. We have two main reasons why reactions are faster at higher temperatures. The first one is what I just talked about, is that more molecules have sufficient energy to get over the energy barrier. So there's a really large effect, so they can actually go from reactant to product if they have enough energy to go from reactant to product, meaning they can go over that activation energy barrier. But the second thing is more molecules actually have collisions, and technically Irenaeus, who's the guy who came up with all this, he really ignored collisions. But we're better chemists than that, so we're going to take a little look at collisions and figure out how that has any effect on reaction rate. Remember, the whole point of this lecture is to figure out how energy and kinetics really come together here. So for Arrhenius law, we have that the rate constant K increases with increasing temperature. This shouldn't be too surprising. When the temperature goes up, that means we are at higher kinetic energies, which means we're at higher velocities, which means we're having more collisions. Therefore, we are allowed to go from reactant to product at a faster rate. So that means if you increase temperature, you're really going to be increasing your rate constant. And since the rate constant always has a direct relationship with your rate, that really means you're increasing your rate of your reaction. Okay, so it's all very important, this kind of string of thought. Now the second thing, at higher temperatures, which we just talked about, more molecules have enough energy to make it over that energy barrier, so the reaction goes faster. Okay, this all makes sense. And so if we were able to put this into an equation, we can come down here. And so we get K, rate constant, what we've been talking about for the last 6 episodes, 7, I don't even know what number we're on anymore. So K is equal to A, I'll come back to this in just a second, and then we're going to say E raised to negative EA, activation energy, divided by RT. So K is your rate constant. We know that the units change on your rate constant. So you need to look at the order. Is it 0, first, or second order, and what time component? Seconds, minutes, days, what are we looking at? Like I said, we'll come back to A in a second. EA is your activation energy. We already drew that out, so you know what that looks like. The big thing here is that in the equation, you need to make sure you use joules per mole for your unit. Just like we talked about with a lot of other things that use R, usually we give you activation energy in kilojoules per mole, so be aware of that. Make sure you convert your unit from kilojoules to joules when you put it in the equation. T is temperature, so we're obviously going to use Kelvin because it's one by itself. And then R is our standard R constant whenever we're using the unit joules. So we've got 8.314, and that unit is going to be joules per mole Kelvin. Okay, so let's look at A. What is that A? A is called the pre-exponential factor. Okay, pre-exponential factor is called A. So the pre-exponential factor A is the rate constant, so it's technically a little k. It's the rate constant at infinite temperature or the theoretical maximum reaction rate possible. Whew, that's a mouthful, right? The way I like to think about it is that it's in the perfect conditions. So we are trying to figure out how fast this reaction is going to work when you're under perfect conditions, when it's super hot, when you're in the perfect medium, when you're at great concentration. How fast is this reaction going to go? And so I like to think about this as like a rom-com for those high school movies, right? The terrible ones. And it's like you always get this like perfect kiss at the end, and the girl's walking out the door, and she's running away from the guy, and it's pouring rain, and he yells like Sarah or whatever her name is, and she whips around, and he grabs her, and they have like the perfect kiss and the perfect moment. That's what pre-exponential factor is. It's like the perfect set of conditions for the chemistry to happen, okay? So that's what you need to think about. It's going to be a rate constant. It's going to match your unit of K for your rate constant. So you just have to make sure, like, under perfect conditions, how fast would this reaction go? That's what you're saying. Now, here's the thing that we're going to dive a little bit deeper into. Even if all the molecules have sufficient energy, not all interactions between reactants will lead to products. Like, what is that about, right? So what we're going to do is dive through an equation, a specific equation. And so I've got an example here for you. I've got nitrosyl bromide, and it's going into the bromine molecule and 2 nitric oxide molecules. Okay, so we've got this big complicated equation. I also have made little signs so I can act this out for you. I hope I get this on screen. I can't really see where I'm at, but hopefully this is on screen for you. And so I will show you how this works because I'm a visual person, and if you're a visual person, this should be hopefully easy for you, but we'll see. Okay, so the first thing we want to think about is head-on overlap. So we've got one molecule here. Here's our bromine. And I'm going to flip this upside down so it works. And so we have our bromines coming at each other. And so what happens here is our bromines are like, yeah, I want to hang out with you. You're super cool. And they decide to leave the NO groups. Okay, so we're going to kind of fold that up. We're going to take this bromine, and we're going to fold this up as well. And then let me just flip it around. I'm going to cheat, okay? So we're going to have our 2 bromines together. They now just made a bond. They're a molecule. And then our NOs, because that bond was split, they can just kind of like float off into space. But this is only going to happen when our bromines come at each other with head-on overlap. Okay, so that we know for sure is going to work. Now let's look at another set of conditions. Let's flip this one around. So now I've got my oxygens coming at each other here, like this, okay? Do I have that? Yeah, okay. My oxygen are coming at each other. So now, what do we know about oxygen? And this is where if we were at an 8 a.m. class, you'd all be yelling, it's the second most electronegative atom in the entire world. I'd be like, oh my gosh, you guys are so smart. I love you so much. You're amazing. Okay, so now that we got past that, do you think two oxygen atoms are going to want to come together and form a bond? No, right? They're sitting with two other atoms, bromine and nitrogen, that are significantly less electronegative than it. Well, nitrogen not so much, but bromine definitely. And they're less electronegative, so what that means is that this oxygen can suck all these electrons from nitrogen and bromine, which it would not be able to do if it was partnered with another oxygen. So these molecules are not going to react. If they bump into each other in a beaker, it's literally going to be in elastic conditions. They're going to slam into each other and be like, peace, not interested, and then just swim away. Okay, so this orientation, if they hit like that, no reaction. But then if you remember from valence bond theory, we don't only have sigma overlap, okay, or head-on overlap, we also have side-on overlap, where our two p orbitals came together to form a pi bond. So in this example, that's like having our species come together, okay, like this. And so our molecules come together, boom, slam into each other. So now, we already talked about the fact that our bromine atoms like each other, so they're going to want to form a bond. These two bromines are going to come together. They like that. But these nitrogens are like, no thank you. We don't want to be bonded at all. So what happens then is these bromines then basically split off. So the two bromines can then float away together, and then each of the NOs are by themselves, and they can float away as well. And so that's kind of how that reaction works. Okay, so now, if we put this all together, we can see that the orientation completely matters. It's not just about temperature and how fast it's going, it's how these things interact. Same thing as like if you walked by a really hot guy, it doesn't matter if you don't see him, if you don't like use your eyeballs, if your back just sees him, it doesn't work, right? Okay, so now, this brings me to Irenaeus Law, which gives us the beautiful equation that you actually would use in lab. So if you continue on with chemistry and you do any type of kinetics, you're going to see this equation and you're going to use it a lot. So Irenaeus Law is written as an exponential. But if you take the natural log of both sides, there is a linear relationship between the natural log of k, rate constant, and the inverse of your temperature. So all I'm doing is taking the equation I gave you like 3 or 4 slides ago, and I'm just adding this component to it. I'm adding the natural log piece. Well, when we do that, we can get this thing called the Irenaeus plot. And this is something I had to do in grad school all the time. So if you've watched the other episodes, I was telling you about how in grad school, what I had to do was measure my catalyst reactions in terms of the kinetics. And so what I would do is I'd measure how long it took my reactants to turn into products. And then from that, which you'd have to do like 3 times under all the different conditions, from there you'd be able to calculate your K or your rate constant. Once you know your rate constant, you have to triplicate that data, make sure you can repeat it. After that, you run that exact reaction under like 5 or 6 different temperatures, and you get an Irenaeus plot. So you actually plot this thing out. And so I have this in so many of my papers and dissertations and stuff. Like, this is my bread and butter, because without this you can't publish it. Remember before how I told you without K you can't publish, and without that you actually can't publish without your activation energy. That is the thing you absolutely need in order to publish something on kinetics. So how do you get that? Well, you take your natural log of your K and you're going to plot that on your y-axis. Then you're going to take your inverse of your temperature and you're going to put that on your x-axis. And so what you're going to see is you can actually plot this. You're going to get a straight line plot if your data is good. If your data is not good, you're not going to get a straight line plot. And what you're going to see is that your slope is equal to negative activation energy divided by R. My eraser's not working for some reason, that's okay. So your slope is equal to your negative activation energy divided by R. And so what the y-intercept is going to be your natural log of A. So all the way up here, that's your natural log of A. Remember, A is your pre-exponential factor. That's what that is. This isn't concentration here. I know it's confusing that we use A for both of those, but it is what it is, so you just got to know the difference. So here you can actually determine what your pre-exponential factor is. So let me give you a problem. Using the same data that I just showed you, what is the activation energy for this reaction? So if you got all this data in lab and now you have to go report it in a paper, what would you say your activation energy is? Okay, so the first thing you're going to do is realize that your slope is going to be equal to your negative activation energy divided by R. So you're going to go over here to your plot, and you're going to take your slope, which is negative 1.2 times 10 to the 4th Kelvin. So that's going to be here, negative 1.2 times 10 to the 4th Kelvin. you're going to set that equal to negative EA, activation energy, divided by R. We're talking about energy, so it's going to be 8.314 joules per mole Kelvin. So if you put that into your calculator properly, you should get your activation energy equal to 99,768 joules per mole, which is equal to 99.8 basically kilojoules per mole. So remember how I told you that we usually report activation energy in kilojoules per mole? Here's a classic example for you. So if you were going to go take this and plug it into the equations we talked about previously, which are actually on my next slide, so I might as well go there. So if you were going to take that value and try to plug it in here, you would need to remember to convert yourself from kilojoules back into joules in order to use this equation, okay? Now, what we want to do, though, is to be able to actually look at two different samples, and we want to compare them and say, now, I did all my studies on, room temperature. Everything's at 25 degrees Celsius. How is my rate constant going to change if I raise my temperature to 35 degrees Celsius? So again, this is something that happens all the time in labs. We do kinetics all the time in medicine trials, in like clinical trials. That's what I'm trying to say. They do this all the time. Kinetics is so important. So what you do is you take both of these conditions, and so you can set everything in here, set everything in here. You can solve for A, set it equal to each other, because A is the same. Remember, it's run under perfect conditions, which is like the hottest it could possibly be at before the molecules, specifically your reactants, start to decompose. So you can set these equations equal to each other, and when you do that, you can derive what's referred to as the Irenaeus equation. For my students, you're like, oh my gosh, I recognize this. We have seen this at least 2 other times in the class this semester. Remember, our Clausius-Clapeyron equation and our Van Hoff equation looked exactly like this. This is just the 3rd time you're seeing the same type of relationship. So by now you already know this one, but just in case maybe you skip that section or something. All right, here we go. R 8.314 joules per mole Kelvin. That's always going to be the case because we're talking about something with energy. Again, remember that this is going to be in joules per mole, but likely off of a table it's going to be in kilojoules, so convert back down to joules. We've got temperature. It's by itself. It's absolute instead of being delta or the change, so it's got to be in Kelvin. You have no other option. K, as long as they match. Okay, your units must match. Okay, it is the same reaction that you're studying, so it's not like it's going to convert from first order to second order in the middle of changing temperatures. That's not how chemistry works. So it's going to be first order throughout or second order throughout. So your unit is going to be dictated by the order. Once you have the order, you can then determine your unit and then plug it into the equation as long as they match. Okay. So this brings me to transition state theory, specifically meaning we're going to draw this out. So what you're going to see is the same reaction we've been studying over and over and over again all through all these episodes. So we've got our methyl chloride, we react it with our hydroxide ion, and then we form our methanol and our chloride ion. Now, what I was describing earlier is this transition state right here. Your transition state is not an intermediate. It's not a real product. You can't isolate it. You can't characterize it. It's something that's so unstable because if you can see here, we have methyl connected to both the hydroxide and the chloride ion. That is not something that is ever going to happen because that carbon is now bonded to 5 different things, and we know carbon always obeys the octet rule. Okay, so we refer to this as a transition state. So we put this little symbol right there, and so it's like the not equal to sign. It's the same thing. We put that at the top. Usually, if you come down here in the plot, you're going to see this written at the top. If the molecule wasn't there, you would see this symbol written directly over the molecule. So here what we see is our reactants are going to products. We can see here from our delta H that this is an exothermic process. That's your thermal part. And then your kinetics part is right here. So your delta G, your change in your free energy of the transition state. That is actually also equal to your activation energy, like we said earlier. So it's the minimum amount of energy needed to go from reactant to transition state down to your product. So when we talk about activation energy, we're really talking about how much energy is needed to go to that transition state. It's not really to your products, it's the transition state. So you might have noticed that I was dancing around that terminology earlier, and that's because of this right here. It's how much energy is needed to make that transition state. All right, so let's look at an example here. The first one, here is a one-step mechanism, so it just goes from reactant to products. Now this one is a two-step process, and you can probably see that by the fact that we have one bump, it levels off, and then another one. So right away you can come over here and draw a line right through that spot. So on the left side we have step 1, and then on the right side you have step 2. Again, you have your reactants here and your products here. So we've been studying how it goes, or what it takes to go from methyl chloride and hydroxide to your methanol and your chloride ion over here. And it looks like got some extra numbers in here. Okay, whatever, just kind of ignore that down here, guys. Okay, so we've got step 1 is going from our reactant to our product, and so we can see our transition state right here is going to be that molecule that has many bonds. It's breaking one bond, making another bond, so it's at that transition state. We can see the activation energy of step 1 is right here. Okay, the change in the energy from the transition state to your reactant, that's your activation energy. Now your intermediate is right here at the bottom. This spot, that's your intermediate. Okay, remember how we said in the last episode that intermediates are not reactants and they're not products, but they're made in the middle. So they're product first and then they're a reactant, but they're not overall. Okay, they're not in the overall reaction. So then your intermediate then reacts and forms the product. So in step 2, you have another activation energy barrier. That's right there. So activation energy 2. So overall, you can come over, I'm over here on the left side. Now what you can see is that your activation energy of 1 is much, much, much bigger than your activation energy of 2. So if I were to ask you, what is going to be your slow step here in this two-step mechanism, hopefully you would look right at this huge activation energy and say that step 1 is going to be your rate determining step, RDS, your rate determining step. As we said last time, it could also be rate limiting step. Either is fine for me, okay? So then you see you go from reactant to transition 1 to intermediate to transition 2 to product, okay? So now what I want to do is give you 3 different questions in a row. For those of you who printed the slides out ahead of time, you have all these for you. I will read them for you for those of you who did not. But for the first thing we're going to do is look at this mechanism right here. And I'm going to ask you 3 questions. The first one is, how many steps are in this mechanism? The second one is, how many intermediates are in this mechanism? And then the last question is, what is the slow step? So how many steps, how many intermediates, and what is the slow step? I actually want to throw a bonus question at you, and I want you to tell me how many transition states there are as well, okay? So take a few minutes, please pause the video and see what you can come up with. Okay, this is a 3-step mechanism, 3 steps. We can see it right here, where you have a flat part and a flat part. Draw your line right there to separate your steps. We can see step 1, step 2, and step 3. So you see there's a flat little piece. So every time you have a curve, that's a step. So you have reactant to something, B. And then you have step 2 right here, which is your second step. This thing, B, moving to C, another thing that we're going to answer in a second. And then when we have C going to D, that is your third step. So there's 1, 2, 3 steps in this mechanism. All right, next question. How many intermediates are there? That's what I was dancing around. There are 2 intermediates. B and C are your intermediates, so 2 is the correct answer here. Remember, an intermediate is temporarily formed. It's a real molecule. It exists. It doesn't have like several different bonds going around from it. So it has to be at a leveled, plateaued off part. It's not at a peak. It's at a bottom part in this Arrhenius plot, okay? So 2 intermediates. Next question. Which one is the slow step? So you're really looking for the step with the greatest activation energy barrier. And so when we go from A to peak, we don't have that big of an activation energy barrier, EA1. It's big, but it's not that big, compared to intermediate B going to transition 2. And so that is going to be your second activation energy barrier. And then your third step is going to go from intermediate C up to the peak right there, and that's going to be your third activation energy barrier. So what we see is that activation energy 2 is much, much, much bigger than activation energy 1, which is just much, much bigger than activation energy 3. So which one is the slow step? It's the one associated with activation energy 2, which is the process of intermediate B going to intermediate C. Okay? I did ask you to have a bonus question in here, so we can go back to this one. I asked you how many transition states there are, and that would be 1, 2, and 3. So hopefully all this makes sense. If not, that's the beauty of these videos. You can pause them and go back and try to figure out like what's not making sense. Please, if anything is unclear, come to our Zoom office hours, schedule a meeting with us, use Piazza. We are here to help. We want to make sure you guys get this stuff down, okay? Good luck, take care of yourself, and drink water.